And now for a quick summary on physics and integration. Integration is an essential skill for mechanical physics, as it allows for many different quantities such as force, energy, acceleration, velocity, and displacement to be related to one another. And the sum of all forces acting on an object is called the net force. It is equal to mass times acceleration of the object. Work is the transfer of energy into a system over a given distance, and is equal to the product of the net force and the displacement. Because work is equal to force times distance, we can calculate that force is the derivative of work with respect to distance. From this, we can integrate both sides with respect to distance to figure out that work is the integral of net force over the change in distance. This is an important formula for work, and it should be memorized. Another important formula is that work is the change in kinetic energy. First, the displacement function can be plugged into the work integral. The integral must be made with respect to time, so the derivative of the position function can be taken, the dx singled out, and the result plugged into the equation. The force is equal to mass times acceleration equation, where acceleration is the derivative of velocity, can be applied. The equation must be integrated with respect to velocity. So the derivative of velocity is taken, dv is isolated, and the result is plugged into the equation. The integral is then evaluated, and the result is equal to the final velocity minus the initial velocity, which is equal to the change in velocity. This is another important work formula, and it should be memorized. Now, for a practice problem. In this problem, we are lifting a leaky sandbag that initially weighs 144 pounds. The bag is half empty at 18 feet. Calculate the work required to lift the bag of sand initially on the ground to 18 feet above the ground, and assume that it leaks at a constant rate. To begin, we will calculate that the force must be the weight of the bag multiplied by however much is left in the bag. We know that at 0 feet in the air, it is 100% full, so it will be multiplied by 1. Because we know that at 18 feet in the air, the bag must be half empty, we know that when x is equal to 18, we want the entire equation to be multiplied by half. So a fraction that works like this is 36 minus x over 36. Next, we can multiply out the constants, which in this case would be the weight, 144 pounds, and the divided by 36. Next, this equation integrated, evaluated, and the result comes out to be 1,944 foot-pounds. Derive an equation for the work required to pump all the liquid out of a cone-shaped container, with the point facing downwards that is p% full, height-wise, h feet tall, and has a radius of r feet at the top, where the liquid has density d. Now, to do this, we're going to have to take an integral from the bottom of the cone to the top of wherever it is water, and figure out how much force is required to pump that much water out. Now, we know that the cone starts at 0 feet, so the bottom of our integral will be 0, and we know that it will end at the total height of the cone multiplied by how full it is, percentage-wise. So that is h multiplied by p over 100. The amount of force required to pump out any given layer will be the cross-sectional area at that height multiplied by the density of water. Now, because we know that the cone has a cross-section with a radius height multiplied by r over h, the ratio of radius to height, and we know that the area of a circle is pi r squared, we can plug our radius, which is xr over h, into the pi r squared equation. So we get work is equal to the integral d pi x squared r squared over h squared dx. Next, for simplicity, the constants can be factored out, and then the integral can be evaluated. We know that the bottom is 0, and anything multiplied by 0 is 0, so we can neglect the bottom, and instead simply take the integral and plug in ph over 100. So taking the integral of x squared, we get x cubed over 3. We plug ph over 100 into x, and then we multiply it all by d pi r squared over h squared. And in the end, we get d pi r squared p cubed h over 3 million foot-pounds. And that is the end of this video.